We're going to finish up Chapter 17 slides today so that we can dedicate our class time on Monday to the final exam review. So this slide is a summary of the last two problems we did during our last class. We were investigating the molar solubility of magnesium fluoride under different conditions. To remind ourselves, molar solubility is the maximum concentration of an ionic solid that can be dissolved into a solution before the solution becomes saturated. Or we can think of this as the maximum concentration of the ionic solid under the conditions of the solution. We saw that in pure water, magnesium fluoride has a molar solubility of 2.6 times 10 to the negative fourth molar. We also saw that the same compound was less soluble if it was added to a solution already containing 0.1 molar sodium fluoride. The molar solubility of magnesium fluoride under these conditions decreased to 7.4 times 10 to the negative ninth molar. We identified the reasons for this decrease in solubility was because magnesium fluoride and sodium fluoride both share the common ion F-. By increasing the concentration of F- in solution by the addition of sodium fluoride, we have shifted the equilibrium of the dissolution of magnesium fluoride back toward the left and thus precipitating out magnesium fluoride. This effectively lowers the maximum concentration of magnesium fluoride that can be dissolved in the solution, so decreasing the molar solubility. We have shown mathematically that MgF2 is less soluble in a sodium fluoride solution when compared to that of pure water, and we have also rationalized the effects by using Le Chatelier's principle. Just as we predicted using Le Chatelier's principle, we can see graphically that the molar solubility of magnesium fluoride decreases as the concentration of sodium fluoride increases. On the y-axis is the molar solubility of magnesium fluoride, and on the x-axis is the concentration of sodium fluoride in solution. Just as we predicted, as the concentration of sodium fluoride increases, and consequently the concentration of the common ion F- increases, the molar solubility of magnesium fluoride decreases. The common ion effect does not just necessarily impede the dissolution of ionic compounds, but some ionic compounds react with acids and bases, and that can increase their molar solubility. In the case of calcium carbonate, we can see that the concentration of as the concentration of hydronium increases, or in other words, as the pH decreases, the molar solubility of calcium carbonate increases. We can rationalize this using Le Chatelier's principle. By increasing the concentration of hydronium in solution, there are too many reactants and the equilibrium is going to shift toward the products. This increases the molar solubility of calcium carbonate. So we've dealt with a lot of big K's, or equilibrium constants, in the last month. We've had Kc, Kp, Kw, Ka, Kb, and now Ksp. As with all equilibrium constants, we can calculate the reaction quotient to determine which direction the reaction will proceed in order to reestablish equilibrium. When dealing with Ksp, and since this deals specifically with the dissolution of ionic compounds, Qc has been renamed Ip, or the ion product. There's functionally no difference between Qc and Ip, it's just a different name for the same thing. Since Ip is entirely analogous to Qc, the same pattern should emerge when we compare Ip to Ksp as when we compared Qc to Kc back in Chapter 15. When Ip is greater than Ksp, the concentration of the products is large or too large, and the equilibrium will proceed back towards the reactants or back to the left of the reaction. If we look at our magnesium fluoride example, we can see that solid magnesium fluoride will form in this case. And as we observe this, we will observe this as a precipitation of the ionic solid. When Ip equals Ksp, equilibrium is already achieved and nothing happens. Magnesium fluoride remains soluble, but it will be in a saturated solution. Any addition of magnesium fluoride to the solution will not increase the concentration of magnesium 2+ or the F- in solution. When Ip is less than Ksp, the concentration of products is low and the equilibrium will proceed toward the right. This will pull the reaction toward the products and magnesium fluoride will then dissolve into solution. The solution is not saturated and any additional magnesium fluoride solid will be continued to dissolve until Ip equals Ksp. The last topic I want to touch on in Chapter 17 is increasing the solubility of ionic compounds via complex ion formation. Silver chloride is sparingly soluble in water with a KSP of 1.2 times 10 to the negative 10th. We see that in the picture that the vast majority of the silver chloride remains as a solid at the bottom of the beaker with a very low concentration of ions in solution. Upon the addition of ammonia to the solution, however, we see that the silver chloride's molar solubility is increased and the solid is dissolved into solution. So how did this happen? Ammonia can form a complex with the silver cations to form a silver ammonia complex ion. The complex formation is soluble and the equilibrium is heavily favored towards complex formation. As we can see with this large K value, 1.7 times 10 to the 7th, for the complex formation reaction. I have labeled the second equilibrium as just K, since this is not technically a KSP type reaction, but rather a complex formation reaction, but the same ideas of equilibrium constants apply. So in reaction 1, the dissolution of silver chloride into its constituent ions, and reaction 2, the formation of the silver ammonia complex, are linked through the common ion Ag+. This common ion acts as a bridge between the two reactions, and that's why the silver ammonia complex formation can drive the dissolution of AgCl into solution. As can be seen in the illustration, Ag+ no longer is found in the solution alone, but rather all the ions are complex with ammonia. As we did in our previous examples, we can graph the changes in molar solubility of silver chloride in relation to the concentration of ammonia in the solution. On the y-axis we have the molar solubility of silver chloride, and on the x-axis is the concentration of ammonia. As more and more ammonia is added, more silver plus is complexed, and the reaction equilibrium is pulled toward the right to increase the solubility of silver chloride overall. So this concludes the end of our slides for Chapter 17, and I'll see you all on Monday for the final exam review.